So, without further ado, let me introduce our distinguished speaker, Burak Göktürk. First of all, we thank him for coming to this conference. We've met Burak a few years back in another conference, and I have to say that he's probably one of the most humble persons that I've met. Maybe one of the most successful entrepreneurs among Turkish engineers. I don't know if you remember seeing in the news that he founded like.com. And how much did you sell it for? About $100 million, something like that, dollars, to be clear. To Google. Burak Göktürk is the Vice President of Machine Learning Systems and Cloud AI Research at Google. He leads AI and systems research for Google Cloud. His responsibilities include developing algorithms for enterprise AI solutions, integrating AI into systems research, and overseeing the development and real-world application of machine learning technologies like generative AI-based large language models and agents and agentic systems like co-scientists. Previously, Burak headed the Vertex AI and developer teams, creating AI products and solutions for enterprises and developers, including those requiring minimal AI/ML expertise. This portfolio included the Vertex AI platform for large models, agents, search and grounding solutions, and developer tools like Kaggle, Colab, and AI Studio. For 13 years prior, he was Vice President of Google Shopping, focusing on commercializing computer vision and machine learning within the shopping domain, both in ads as well as search. Before that, Burak was CTO, CRO, and co-founder of like.com, as I mentioned, where he drove exponential revenue growth with an AI-based product discovery technology. He also led algorithm development at Canesta, Intel, and Beko in past. He has roughly 30 years of AI and machine learning experience, more than 100 publications and patents. He holds master's and PhD degrees in electrical engineering from Stanford University, and he has a double major in electrical engineering and computer science from Boğaziçi University in the previous century, I think. Without further ado, I thank Burak again for joining us today, and the floor is all yours.
Thank you so much. It's such an honor as well as such fun to be here. It's always a great opportunity to come visit our country. So, thank you for the introduction. I think you went through, more or less what I've done throughout my life. But currently, I'm leading lots of research activities within Google and within Google Cloud, focusing on AI and also focusing on combining AI and systems research together as well. So today I'd like to talk quite a bit about the trends that we've been seeing when it comes to AI. And I'll also tell a little bit of some of the stories, even going all the way to my days in both undergrad and PhD, and how we've come to this area as well. I was talking with the owner. I think we'll take some questions at the end, maybe. So please try to keep your questions towards the end. So I think, especially when ChatGPT came, everyone realized all of a sudden, oh my God, AI can do much more than we thought it could do. If you thought like that, like just maybe raise your hand for a second, right? Even the people who were working on AI actually thought that a little bit. When I was doing my PhD, with my friends and with my colleagues, we were doing some predictions on where AI would go in 10 years, 20 years, 50 years, 100 years. And I think maybe in 20 years, it progressed what we thought it would have progressed in 100 or 200 years. It progressed really, really very, very fast. And then what caused this? I think Google internally had systems like ChatGPT, actually, but we did not release it. Also, because we wanted to be really safe and very ethical, very sure about all aspects of a tool like ChatGPT. Of course, after ChatGPT, Google as well as many companies followed as well. So there are many reasons why all of a sudden it really picked up so fast. And if you look at the core algorithms that are being used, they're not very different from 50, 60 years ago. So if I were to give one example, really the very core algorithm is neural networks. It's from the last century. And I think many of you might have heard about it. It has some inputs, and then it really does simple operations of additions and multiplications in these like hidden layers, getting some input weights and outputting some output weights, and then with comparison to some threshold numbers, it gives some decisions. That's as simple as that. And then these weights are, through various optimization algorithms, are optimized for some maximization or optimization function. So the logic is relatively simple. And when I was at Boğaziçi University, I started some of my early explorations with AI. Then I followed, as Onur mentioned, to California, to Stanford, where with my peers and colleagues and my professors, especially with my friends, we were even asking ourselves, why are neural networks even in the textbooks? Because they perform the worst compared to any of the other AI algorithms that we were trying. At the time, support vector machines was a very popular machine learning algorithm, but it didn't perform even as good as many of the simpler linear algorithms, linear regression, or other AI algorithms. So at the time, we were even thinking, why is it even in textbooks? It doesn't perform at all compared to all the other AI algorithms. But we missed on a few things. One, it's very parallelizable compared to many of the other AI algorithms. Many of the other AI algorithms are much more dependent on matrix algebra and matrix multiplication, etc. It's not as easy to parallelize into hundreds, maybe thousands or tens of thousands of machines. But when you look at neural networks, both the model itself as well as data is very parallelizable. So that was the number one thing that we missed. Maybe we missed in a big way. Okay, you can parallelize, that's great. But when I looked at even my PhD thesis was, for instance, on detecting cancer from computer tomography images. I was working with about 40 patients' data, 40. So I didn't really have much data at all. So parallelization really didn't help then. Like, you need lots of data for parallelization to be useful. For 40 pieces of data, you don't need to divide it into 1,000 machines. In one machine, it was SGI machine at the time, it took about 45 seconds or so to do the full training. So it didn't take too long time either. So you didn't really need the parallelization. The second thing that I think came, that I find it somewhat revolutionary, is that we figured out how to create training sets, huge amount of training sets for neural networks to be trained in parallelized machines, thousands of machines, tens of thousands of machines, maybe more. And the concept is pretty clear, actually. First of all, thanks to internet, over this time, there is lots and lots of data over there, right? Billions of pages. So the trick is very, simple. You take words, from anywhere, but internet corpus is a big one, and then you start masking words. For instance, Istanbul is the largest city in Turkey, right? You start masking words from a sentence. Let's say you start masking, the third word. Istanbul is the blank city in Turkey. So there, the training set is that, okay, this is a question, fill in the blank, and the answer is also given. It's in the training set, it's in the ground truth, which is the largest. It's all coming for free from internet. So here we go. All of a sudden, you have trillions of pieces of data samples, and you have millions of machines to parallelize and learn. And that's how, all of a sudden, we see this exponential growth in understanding when it comes to computers and AI. And of course, the algorithms have changed a little bit as well, but it's still, in the core, it's neural networks. The most recent algorithms that's being used in almost all of the large language models that you see today, from Gemini to OpenAI's models to DeepSeek's models, etc., is this transformer architectures, where I think the trick is in neural networks, instead of forcing the state and looking at only some of the layers, you say all past representations and attend to them. Like attention is all you need is one of the famous papers on this one as well. But short story, it's very much neural network based. But what we missed was A, you can parallelize, B, you can actually create lots of training data so that the parallelization is useful. Combined, now we have all the large language models and this new AI revolution. Sometimes during this talk, or even in my day-to-day life, I say new AI versus old AI. And when I mention those, I think I call this large language models. Some people refer to it as generative AI, as the new AI, and the traditional AI algorithms as the old AI. And when I talk about the trends, you will see me referring to them in that way as well. So before my research role, I've been leading the cloud AI, which is the main enterprise AI solutions that Google has been providing to the market. Both in my current role and in that role, we've been talking to many different customers. So most of the learnings that you see in this presentation are all coming from these discussions as well. So let me actually take a moment here. This is Google's platform for AI. It's called Vertex AI. But if you go to any platforms, you will see something similar to this. And if I were to summarize, first you will see what we call a collection or garden of models. And in Vertex AI case, in Google's case, we have Google's models, we have open source models, as well as we have some partner models all in one place as well. The idea is you can come to one platform. You have the choice and flexibility. Just choose what you want. But these are what we call the base models. These are models that are trained typically on publicly available data from internet by different providers, Google, etc. Llama, for instance, from Meta or DeepSeek's models, they're all there. Now, the next layer is what we call model builder. Now, once you have a large language model, when you're building an application, sometimes you can just take it and use it, and it's good enough for your application. In many of the other times, though, you would actually need to customize it for your own use, for your own application and data. And then that's where this model builder layer, and different platforms might name it differently, but you might have heard things like tuning or fine-tuning or distillation, which is essentially taking these base models that Google or OpenAI or DeepSeek or Meta, more or less poured lots of money to generate, and then you customize it for your own use cases and applications. Another aspect that is pretty critical here is what we call distillation. So large models or large language models, by definition, are large. And the two main artifacts that you will see when you're using a large language model, which is really large, is A, the cost really goes up. And B, it's much slower. So if you have an application, well, first of all, if you have budget constraints, but more importantly, if you have latency constraints in your application, you would actually want a smaller model. But then as the models get smaller, their reasoning and thinking abilities start going down. Because you start losing this, remember the whole parallelization effect and lots of data and how neural networks became the best? You start losing it a little bit because as it becomes smaller, it's losing that advantage. So how do you go about it? The trick is what we call distillation. You take one of the large models and you distill it, you make it smaller to produce a smaller model. That's what we mean by distillation. This way, you get a smaller model that fits actually well to your own maybe use case and data. So it doesn't necessarily perform well on everything, but it performs well on your own use case. So that's why this model builder is really, really important. Most of the time, you want to customize these models to your own use case. And the last one is what we call agent builder. And I'll talk quite a bit about agents today because the last 1.5, 2 years, we've been talking a lot about large models and large language models. The future is going to be much more about agents. And I'll tell what it really means. For now, think about applications, building applications on top of large language models. But they need to be customized and they need to be able to use other tools other than large language models. They need to be able to use search, for instance. For instance, if you're building a hotel booking application, they need to be able to call a database to be able to get the availability of hotels. They need to be able to call a payment system to accept a payment and actually make the transaction. So they need to start using other tools other than large language models. And that's why a good platform also needs to have all the tools that you need to have to build these agents. So we'll talk on some of these in more detail during the talk. But maybe one thing to mention is that more or less all the companies, this is not specific to Google, but everyone is seeing an exponential growth in API calls, in calls to these large models or large language models. And this was from an earnings statement, actually the last earnings statement or the prior. It was a 14 times growth in 6 months. You see that kind of growth in more or less everywhere when it comes to large language models. Demand is something that no one has ever seen. On the other side, supply, which is supply of chips and supply of energy to some extent, is, especially chips, let's talk about chips for a second, is coming at a much smaller pace, much smaller growth rate from any company. So I think one problem that the world needs to deal with is how to make running of large language models much more efficient. So that using the same chip, instead of running one call, you can do 10 calls and things like that, because the demand is going so much faster than the supply in general right now. Okay, now let's look at, I tried to organize some of these thoughts into trends. The very first trend, and the obvious one, AI is moving so much faster. I think you're all realizing that. Let me mention maybe 2 reasons for that. One, the amount of data that is needed to build any application, any agent, has come down drastically. So previously, using traditional AI, you or a company, when they want to build an application, typically they would need to go and collect their own training set. And especially for an enterprise application, sometimes it's meant many months, sometimes year just collecting the data, checking the data. Usually the data will be very noisy, so they will need to reiterate again and again. And then eventually they start training the machine learning algorithm in the traditional AI methods. Now in the new methods, what happens is the models are already trained by more or less all the publicly available data in internet. In many cases, you do not need to provide even a single piece of data for your application. And in some cases, you might need to provide some for fine-tuning, but it's still a smaller amount of data compared to before. So that's number one. Like instead of taking sometimes months, years, on day one, you already have a model that's already trained with all of the data that's available publicly and already provides very decent results. Second, it used to be that you really needed to be a data scientist, an AI expert, to be able to develop all these AI algorithms. And that's also changing as well. Now, any developer can go back and do an AI application. A middle school student, high school student, they will be able to do that. That used to be not the case 6 years ago, 7 years ago. That has changed completely as well. Now you can imagine the number of people with an AI degree versus any developer in the world, maybe 100 times or 1,000 times difference. So all of a sudden, what does it mean? Everyone is programming AI. And then you see this exponential growth everywhere. So these, I gave the main, as the main reasons why it's moving so much faster. Now let me mention a few technical trends. I think you will find these pretty interesting as well. And even in some of these, I think I and many of my colleagues at Google and other companies were also wrong. We also get to learn some of these as well. But first of all, we initially thought there would be a different model for different tasks. Indeed, even we had a medical model we called MedLM. And then it's an interesting story. We had MedLM. Then a new version of our large language model came along. And the base model of the new version was already better than what we trained for medicine using the old model. So what happens is that as the base models improved, these specialized models that you build on top of the prior versions of the base models were worse than the base models. So that was one interesting observation that we had. But then, as a model provider, the most scalable approach is get everyone to specialize into these different tasks. First of all, a medical model or a finance model also was not necessarily enough. When you look at a finance problem, each problem and each data is a bit different. So you would really want your customer and developers to be able to customize a specific large model for their own exact use case. Just one big financial model wasn't enough. So as a strategy, many of the large language model providers, what are they doing? They're providing the base models and providing all the necessary tool set to be able to customize, to be able to fine-tune those models. So that's one big trend that we've seen, I would say, in the last 1 year. Another one, so I talked a little bit about this neural networks, transformer structures. So in these graphs, both of them are a neural network. Now, dense models is essentially doing all the calculations that are necessary at every single node of this neural network. And remember, I said, well, we need to be much more efficient, right? Demand is going up, supply is going up, but much slower. Number of chips that are generated in the world, produced in the world, is growing much smaller. So we're looking at ways of doing the same calculations much more efficiently. And one way of doing it is what we call it, efficient sparse models, where you essentially make the calculations where needed. And there are many techniques like that we deploy here. But this way, if you need to make the calculations only 1/10 of the nodes, all of a sudden, you're already 10 times faster or more efficient. Another one, and this was specifically something that I thought would be different in the beginning. I thought we would have an image model and a video model and an audio model and clearly text model, etc. Music model that can generate music. What is happening is that we are moving towards a single model that is able to understand all of the modalities. And today we still have some of these separately, but clearly the trend and where we're going is one model that's able to understand both as an input all of these modalities, but also is able to produce all of these modalities separately as well. Perfect. Now the third trend, search. So large language models has their own shortcomings as well. And what we've seen from many developers and many enterprises is that search is one of your best helper, best tool to use along with large language models. So now let's look at a few things, right? Large language models are trained in the past. If you ask for a very recent information, I don't know if you're into, I think many people are into football, soccer in Turkey. I am too. I still watch every single game of my favorite team. So if you asked if Galatasaray is going to get Osimhen or not, and a large language model is not going to be able to know that. Why? It's trained 3 months, 6 months, some time ago, sometime in the past. So most recent information, they're not going to be able to tell you. They're not going to be able to tell you how the weather is yesterday or today or tomorrow. They're not going to be able to tell you the score of the game from last night, etc. So, second, LLMs hallucinate. Sometimes we talk about it as if it's a bad thing. It's actually a feature of LLMs. They're, by design, creative. And also they're very confident while they're creative. So, and that creativity sometimes means it actually tells you data that is not exactly right. It's not super common, but it might happen. And because it's also super confident as well, it's actually somewhat problematic at times. And it's super confident because it still thinks itself that it's actually right. Right? So it's lying to you, but it's so confident that you don't, neither itself or you can understand it is. So third, and this is also very important for many applications as well. Large language models cannot cite, cannot tell you where exactly the data is coming from. It's super good in connecting 10 pieces of documents, 20 pieces of documents, and thinking through them, reasoning through them, combining them, and saying, okay, this is it, this is the answer. And if you ask them, okay, that's great, how did you get there? It wouldn't be able to tell you. Now, many of the end tools, like Gemini Advanced, for instance, are able to tell these now. Why? Because they're also using search as well. When large language models come a bit short, because of some of these reasons that I mentioned here, they start calling search too in parallel, and then start combining the results. And many enterprises or developers they also have lots of private data. Sometimes you might actually want to just search your own private data as well. It doesn't need to be, you need to do a web search. You might need to do a private data. So depending on the application, you would need to do either the web data or the private data. But if you need to take one or two lessons from here, this is probably one of the most important one. Like, never forget about search, and make sure that you have a good search solution also available to you as well through whichever platform that you're using. And in Vertex AI, there are multiple solutions for that. And the big realization here is really LLMs and search need to come together. In many of the end consumer products, it could be ChatGPT, it could be Gemini Advanced. This is actually happening under the hood. That's why, like in many cases, you're actually now able to see where the data is coming from because it's combining with search. Or sometimes, like, you ask the score from last night of a game, and then they would be able to tell it because, again, it's using search to be able to get results like that. And in Vertex AI, we have many solutions. But maybe two things to remember is sometimes you would need web search, like more common data. We call it grounding. Grounding as a term means really combining large language models and search. And in practice, algorithmically, what's happening is that you actually make a query to a large language model. Let's go with the example of last night's game score. Okay, what was the game between this team and that team last night? Let's say Galatasaray and Fenerbahce last night, and who won? And it would then need to do a web search. But in some cases, for instance, a financial institution, bank, like, has lots of private data about companies, etc. And then you wanted to analyze a company and what it should do strategically, or how the company is expected to do, etc. Then you would need to access the data. That's private data, and again, it's a search call, but it's private data access. Now with Vertex AI, you can do both grounding on the data and grounding with Google search. And indeed, we also have a version of the large language model in Vertex AI. Remember, I mentioned it hallucinates because it's creative. We can dial through, using various techniques, it to be less creative but more factual. And we've actually released a version in Vertex AI for that as well. So lots of different tools available. But I think the main takeaway point is that don't forget about search. Search will be a great helper for you. All right, we talked a lot about large language models. And I think, as I said, the next between 1 and 3 years is going to be all about agents. And what is an agent? Like, I think it's a very overloaded term. Even when you look at English, agent is a very overloaded term. Like, sometimes a customer agent. But what I mean, or what many people mean as an agent, is that a computer system, algorithm, tools, etc., that can do beyond what large language models can do, or what large language models can do by themselves. If you look at the first years of applications of large language models, you will see things like summarization, conversations, etc. But you wouldn't see, I gave an example of hotel booking app. You wouldn't see things like that on day one. To be able to build things that go beyond large language models, that's what I call agents. And they need to have certain features. For instance, instruction following, reasoning thinking, probably a small model, application-specific tuning, etc. But maybe the number one thing that I emphasize again and again is something called function calling. People also call it tool calling, tool use, computer use, etc. What it means is, let's think about the hotel booking example again. let's say it's a conversation agent, in an app or on a website, and then you say, as a conversation in English, hey, I want to go to boardroom between this and this date, and I would like to book a 4-star hotel in this price range. So understanding your intent, okay, large language model can do it, but looking up which hotel is available, what are the hotels available in that day, what room times are available, then let you do the choosing of the hotel and the room type, and then finally doing the booking, through putting your credit card. All of these are very different tools than large language models. Sometimes, I think you've all seen the program, I think in Turkey there is as well, Kim Milyoner Olmak İstiyor, Who Wants to Be a Millionaire, right? And there, one of the lifelines is called Call a Friend. So, I sometimes think of function calling as a call a friend. Now, it's a bit tricky, because you would remember also from that competition. It's tricky because A, you need to know that you don't know the answer, and you need to call a friend. And this is so hard for LLMs, because they are confident that they know everything, right? So something like that, understanding that, oh my God, I don't know this, and I need to call a friend. That's already a challenge. Second, which friend do you call? Let's say it's a question about music, and then you call your friend who's a super expert in math. You're not going to be able to get the answer. So which function do you call? So these two problems are still problems that are being worked on in the whole LLM world right now. And again, maybe another lesson to take today. If you're building an application, don't try to overcomplicate it by giving 100 different functions or tools or friends to call. Build something maybe with 5 to 10 functions to call. They're much more better in choosing which friend to call, which function to call, when you give a limited number of options. The moment you go to, let's say, 100, which is still not a huge number, there are trillions of functions and API calls out there. But even if you go to 100, all of a sudden, your success rate might be much less, 70, 60, 50%, depending on which exact model you use. And of course, to build a real-world application, that is not enough at all. So that's maybe one big lesson to take. Again, in Vertex AI, especially on the agent builder side, there's lots of tools, both on the model builder side, various fine-tuning algorithms and distillation algorithms, and also even no-code version of building these tool sets as well. And if you want to build agent itself, we have for developers, there is an agent development kit, which is pretty flexible, model agnostic, and a bit of a, also has an orchestration layer as well. Many of the platforms try to get there, like this, have this agent builder concept and layer. But it's important that whichever platform you choose, if you want to be serious about building agents, you want to have a good set of models, a good model builder for customization, and a good agent builder set of tools as well. Okay, I think I'll go fast on this one, but because I mentioned it quite a bit. In early days, it was really the choice of the model that really mattered. Oh, this is the latest model. This is the largest model. This is the best model with the best reasoning. This is the one that's best in coding. This is the one best in math, etc. That is changing a bit. And there are lots of leaderboards. And this is, I think, from a few weeks ago. But it's changing all the time. What's happening is every other week, another model is coming from another company. And nowadays, we are overly focusing on large language models, and Google's Gemini's models are becoming better by minute. The lesson is, don't settle on just one model. Even if you want to use Gemini models, there are going to be like new models coming almost all the time. But the choice of the platform becomes really important as well. Access to a broad set of models, ability to customize, ability to build agents, all the things that I mentioned earlier. So remember that. Like, don't corner yourself with just one model, because it's gonna constantly change. And maybe something important to mention, we're not getting too much into the detail here, but Imagen and Veo and Chirp and Lyra, when you look at all these, we actually have all the full suite of generative media models as well. For images, videos, speech, as well as music. If you haven't tried, you should go and try those as well. All right, another trend is many of the, especially big companies, are going into more enterprise search and assistant solutions. And for especially companies, and I think institutions as well, agent space is an interesting one, because it really combines search with all the large language model and conversation capabilities with agents, and the ability to be able to build your own agents, as well as use the available agents as well. I think this slide lists as well. Like, it gets so lots of the data is everywhere. Like, especially for enterprises, it might be in an IBM database, a Jira database. Some data could be in Workday, etc. I think the idea is build lots of connectors to all of this data, so you don't really need to worry about where your data lies. You don't need to move your data around. Once you do that, again, you combine the search and models on top to give a really great experience. Combined with all the web grounding or search, like when you're asking about something that's publicly available information, but more recent information, again, combining it with search. And then all kind of tool set, both no code and low code or code solutions, meaning you might be able to design some of these agents without coding at all, just saying in English, like really coding in English or in a language, and also solutions for with coding. And also you can use either you can build your own agents, or you can use some of the existing ones. So, and then you get the final agent space, which is the final UI as well. So maybe I will not spend a lot of more time on this one, but this is another trend that we're seeing, that everyone is looking at ways of making their employees also efficient as well. Like when I go from one meeting to another and I have 5 minutes in between, I can just listen to a summary of the presentation that's going to be provided in the next meeting in that 5 minutes as I walk from one room to the other to go to the to the next meeting. Okay, this part is super interesting, and this is probably gonna give you some stories to tell your friends, family, loved ones today. So I talked a lot about agents. We're also building lots of what we call multi-agent systems ourselves as well. It's essentially an agentic system where it uses lots of tools, LLMs, and even builds different agents and uses each agent separately for the purpose of medicine and genetics and improving biomedical discovery. What does it mean? Let's say you want to take one illness. Let's take ALS. It's an illness that is one of the least known today. We don't know what causes it. We don't know how it really progresses. We roughly know how many years it takes. By the way, I talk to many doctors. They sometimes we call ALS when the person dies in a few years. We call ALS aging when it takes 50 years. So there's also lots of correlation with ALS and aging. So that's, for instance, one of the illnesses that we're focused on. There are quite many, like cancer, leukemia, etc. what it does is it's a multi-agent system. And this slide maybe explains it. It's as if you're going to your research assistant or PhD student. Let's say you're a researcher doctor. You've been working on ALS for 20, 30 years. You go to your PhD student, hey, can you please do a research on this? And then it's a multi-agent system as if the human, the PhD student, is going back and doing that research. So what it does is it reads literature first, right? A PhD student, a human, would probably read between 10 and 30, 40 papers. So this does the same, goes back and reads literature, except it probably reads about thousands of papers, both in that, let's say, ALS illness, but many other correlated illnesses as well. Not just one illness, but so many others. It indeed reads more papers than a human can read in 10 humans' lifetime. So that's one big difference by itself already. Then again, there is another agent that generates ideas. There is another agent that thinks about, what is a validation plan? What is a clinical plan that I would need to do to validate it? There is another one that checks its work. There is another one that looks at ethics and safety. So all of these are agents that are doing like specific tasks for around this. And then it reports it back. A PhD thesis reports it back to the professor, to the expert. Now there is one more interesting thing here. So this is all computers, right? So as a professor, instead of one PhD student, you can have 1,000 PhD students. So you can repeat this process 1,000 times. And then each one of them is producing PhD thesis. And this is all happening, by the way, in one day, which would take humans probably more than 1,000 years, like when you collect all of the PhD thesis that's being produced. Then there's an AI judge agent. All it does is it starts comparing all of these PhD theses. And because it's even for the professor, it's hard to read all those 1,000 PhD theses, right? And then it starts ordering them by literally making a bit of a chess game between each of these ideas. And then finally, it provides the human expert the list of the ideas ranked by the AI agent. A very multi-agent system. Now, so far it's fun, it's nice. I think the most interesting things is the results. So we computer scientists look at the results. We say, okay, this looks interesting. But that's all we can say because we are not medical experts. But for that reason, we've been working with lots and lots of professors from Stanford, MIT, Columbia, and we've been getting very similar results again and again. And I will play one of the videos, Dr. Jose Penades' video from Imperial. This one is an interesting one because they've been working on a secret project for almost 15 years. And then we gave a research proposal. They gave a research statement to us, and then we ran this program, agent. By the way, it's called Co-Scientists, and it's being worked with only some institutions right now. And in one day or so, it gave back results more or less exactly matching his team's 15 years of research, and then provided additional really great results too. So let me try to play this. Okay. So this is a BBC radio interviewing this person, this professor.
When it came up with the answer in 2 days that it had taken you around 10 years to find, what was your reaction?
My reaction, I was shopping with somebody, it was a Saturday afternoon, I was shopping with somebody and I said, please leave me alone for 1 hour, I need to digest this thing.
Wow. Okay.
So, and then the first thing I said is, I wrote an email to Google, say, you have access to my computer, is that right? Because otherwise...
You thought they were cheating?
Yeah, absolutely, because And also, sometimes I use ChatGPT or whatever for improving my English. Also, you have access to this chat. It's a no way, this is all based. It's not just that the top hypothesis they provide was the right one. Okay? It's that they provide another 4, and all of them made sense. And even for one of them, we never thought about it, and we are now working on that.
So we get this kind of response from every single one of the professors that we've been working on, and maybe the next statement that I'm gonna mention is also coming from a genetics expert. He spent his life on it. He's actually Turkish as well. I think he even cured some illnesses through modifying the DNA. It's just that it's very trial and error right now. You don't know where exactly you need to modify in a DNA to fix which illness. But now we know how to modify it. We just don't know what to modify. And for him, it takes 30 years of iteration to be able to figure out one illness. And here's what he said. After what I've seen today related to an AI model, we told him not to talk about it, the name yet at the time. Now he can. Actually, he mentioned that it was co-scientist later. Can't talk about it yet. I can confidently claim that the scientific process will never be the same again. I'm now 99% certain that all diseases, including cancer, will be cured essentially within 10 years. Exponential advance in AI is real. So we don't understand as computer scientists, but when we work with the real-world experts that have spent their lives on things like that, you see the power of it, and if it's used for the right cause, how it can really change the world. And I'm giving an example from medicine, but this actually applies to many other fields. Agents is really the future, and combining large language models with the right tools. For one idea, it does more, co-scientist does more than 1 million calls for one idea. It's constantly thinking. It's as you would do as a human as well, but the results are coming very, very strong. So maybe the last trend is the systems also will need to improve a lot across the world. And here it's much more, I'm not going to go into any details here, but in almost any areas around AI and systems, networking, storage and memory, chip design, the next version of the chips could be AI design. Various things in data centers, understanding that the cables are not, set up well. That takes down some machines for days sometimes until you figure it out. Whereas an AI robot could be just looking at it and saying, okay, this cable is not connected right. Various capacity planning, databases. The data is changing from just words into words and what we call vectors or embeddings, which is computer understandable notion of representations. What is a new query system that can combine the old data and the new data? In the memory case, for instance, a very simple example, there is very, what I call cheap or inexpensive, but very high latency memory, and then there is very fast and low latency memory. But sometimes they're provided to applications in a random way. How can you, using AI, understand a little bit better what the profile of the job is, what the profile of the algorithm that's going to be run, what even the profile of that developer that wrote that algorithm, and then make assignments much more efficiently. So all the systems needs to come up very significantly, become exponentially faster as well. And I think their best tool to be able to do that right now is actually AI too. So you need AI to help systems, and then you need systems to help AI. It's helping each other. So I think this is a quick list of trends that we've been seeing. Hope you enjoyed the talk. I guess we have maybe a few minutes to take a few questions, if you have some. And also, I think I'll be here for a few minutes as well afterwards, so you can come ask some questions as well. But it's, again, thank you, onur, değerli öğretmenlerim, profesörlerim, teşekkürler hepinize, sevgili arkadaşlar, öğrenciler. Çok teşekkür ederim.
How am I going to make sure that the model is convergent? The convergency of the model. This is an important issue, and it's been an important issue for over the years, as far as I know.
Yeah.
Okay.
And convergence also can be taken in multiple dimensions.
Right.
One of them is accuracy. Like, how do we make sure it's accurate? What it's giving is accurate. Right. Another dimension is repeatability.
Right.
Like, and I think you probably have observed it yourselves as well. Like, when you ask the same question again and again, sometimes you get different answers.
Right.
And that used to be not the case with many of the computer systems and algorithms, right? You give a task or you give a question, you give a set of numbers, you get exactly the same set of numbers. And here it's not the case. And I think there is lots of research going on both. And also there's lots of additional algorithms people have put on top as well. For the accuracy aspects, I think combining with other tools, especially search, has been a great asset. For repeatability, I think the main trick that I see people use is sometimes make multiple calls under the hood, and then do a bit of a majority voting or some sort of a voting in between them. And then, like, even before providing the answers to a consumer or to an end user, they would do things like that. But these are well understood and problems. Another aspect of it is explainability. Sometimes, and this is actually even a problem for AI researchers as well. Remember in the beginning I said for my PhD thesis document, it was taking 45 seconds to do the training. And every 45 seconds, I was like, oh my God, I need to wait 45 seconds. It's a lot of time.
It's 40 patients.
For 40 patients, 45 seconds. It was actually nothing. Now, it's depending on the model size, it takes days, weeks, or months to train something. But what does it mean? Every time I made a change in my algorithm in my PhD, I needed to wait about only 45 seconds to get the results. I was getting intuition very, very fast. I was constantly learning, right? And I think we kind of lost it a little bit in that sense. So I had a great intuition at the time of, okay, if I change this is what's going to happen in the training algorithm and how the algorithm is going to change. Now that intuition is coming much more slowly. And that might be one of my biggest fear right now, is that the rate of intuitions, even as the AI researchers who are building the models, is coming very slow. So, and sometimes I make a joke. It works, but we don't know why.
Okay.
So it's not as bad as that, but the intuition rate, the gathering of the intuition is much slower now compared to before.
Okay. I feel like this is an important question. But on the other hand, I've been also dealing with AI structures. Instead of using neural networks, artificial neural networks, it sounds to me that it's more mathematical or more understandable if I use the Bayesian theory. What do you think about that? You can make the Bayesian theory level by level. You can go through. I'm going through the conditional probabilities and the computations.
Yes.
And then okay, this is a very important issue. So I feel confident if I use the Bayesian model. At least I understand the distribution functions and the way it works. Right.
Excellent presentation. I wish I am wondering about that. I'm working in the brain science and coming from the Walter Freeman phase transitions or philosophy. Why don't I don't see any more abstract mathematical representations that they are not used in the, for example, large language models are still just very simple things. About, for example, there is a genus topology in the brain. So, for example, the number of the closed pathways, and so the genus, you know, that maybe Mirzakhani, and late Mirzakhani is a great mathematician. And why don't we use them? For example, I am creating myself in the kitchen, creating more intelligence, but we don't see any such sorts of the things. Could you say?
Of course, I can imagine. This is also something that we always discuss as well. So, a few things. One, in neural networks as well, and the transformer structures, we're still in our early phases. Internally, we believe in the next 3 to 10 years, and I think externally as well, many people say that as well, we will hit AGI, which is like human level thinking capability with computers. And I think for that, lots more innovation needs to happen, even when it comes to neural networks and transformers. Second, some approaches still take some aspects of this traditional AI, which includes some mathematical representations, which is usually in terms of matrix algebra and doing that math as well. And the shortcoming of it's not as parallelizable. You cannot parallelize that into million machines. Is the main drawback that we have something that's super parallelizable. You can feed them trillions of pieces of data. And the other one, the moment you try to make a matrix 10,000 by 10,000, good luck making any matrix algebra on them. So I think combining those two aspects also will need some overall innovation as well. My sight into the future is that the quantum physics and quantum computation is going to hit at some point as well. It's going to come. This might be 10, 15, 20 years. But when it happens, we're going to see yet another level of exponential jump, because even some of these mathematical things that I'm talking about is going to be much more possible as well, because the processing will be super fast.
Can Göknar, I had asked the same question or a similar question in 2023. I don't know if I was satisfied with the answer. Do we know enough about human intelligence or natural intelligence? Because the adjective artificial brings immediately to mind natural intelligence or intelligence itself. Is there investigation going in that area, in that direction? Do we try to know what makes intelligence work? What is intelligence? I don't know the answer.
Yeah.
Forget about artificial intelligence. People ask me what is artificial intelligence, and I cannot answer them.
I think, probably my answer will still not satisfy. But I think the answer is both no, in terms of no, we don't know enough. But yes, in terms of lots of research happening in universities as well, especially around how to model human brain better. Now, we do believe, I think so many experts now believe we will hit AGI, like a machine being able to think as good as a human. It might not be exactly the human brain structure. It's the end result might be the same. And the other issue, I think, that's slowing our progress down a little bit, especially in the university land, is that it became the case is where you need to have chips and resources to be able to do lots of research. And one thing that we're seeing, and we're trying to help as well, is that that access is now much more with companies rather than universities. Whereas a really greatest source of research is usually and still the university. So we're also looking at how do we solve that fundamental problem better? How does universities have much more access to processing power and resources and chips as well? And I think this is going to solve itself in the next few years, because it's going to be super cheap and much more available in the next 5 years. I think it will become so much better as well, because now lots of the research that needs to happen and is continuing to happen is getting a little bit bottlenecked with the availability of processing resources as well, which ties into many different types of research, but including the one that's like psychology and computer science, understanding the brain better. Like lots of research needs to be done, but does require, a little bit of chip power as well. By the way, many people use co-scientists to do research as well. Like they have an idea and come up with like proposals on how I can tackle it, and then they go and do experiments as well. And maybe one last thing, one of our most interesting projects that we're working on right now is called co-scientists or we didn't name it yet, but it's trying to write a paper, all AI generated paper, that gets accepted to a conference which usually has like a 20% acceptance rate or something like that. So maybe. But
thank you very much.
But I think something like that. Well, thank you all so much. Thank you for your time.